When we look for the next frontier, we usually look toward our closest neighbor, Proxima Centauri. But in the universe, close is a deceiving word. This star is 4.24 light-years away, a gap of over 40 trillion kilometers of dead space. To put that math into perspective, if we launched Voyager 1, currently our fastest outgoing spacecraft traveling at 17 kilometers per second, straight toward it, the trip would take 73,000 years. Despite that impossible distance, astronomers locked their instruments on it, and in 2016, they found a signal, a rocky Earth-sized exoplanet orbiting the star, officially named Proxima Centauri b. Every star exerts a specific ring of heat called the Goldilocks zone, the exact orbital pocket where it isn't too hot or too cold, allowing water to pool as a liquid. Proxima b sits dead center in that perfect pocket. It sounds like the ideal setup for a second Earth.
But the actual astrophysics of this neighboring star system turn the promise of an alien oasis into a permanent geographic nightmare. This chart compares the two stars. On the left, our Sun, a yellow dwarf burning at 5,500 degrees Celsius. On the right, Proxima Centauri, a red dwarf with just 12% of our Sun's mass, burning at a sluggish 3,000 degrees. Because the star is so small and cold, the Goldilocks zone is pulled violently inward. To stay warm enough for liquid water, Proxima b has to hug the star tightly, orbiting at just 5% of the distance between the Earth and our Sun. A full year there passes in just 11 Earth days. Sitting that close introduces a fatal mechanical flaw, tidal locking. The star's gravity physically grabs the planet and forces it to stop spinning. One hemisphere is permanently baked under a motionless sun, while the other side is permanently frozen in total darkness. Any liquid water and any potential life would be trapped between these two extremes, a narrow geographical prison called the Terminator Zone, a thin ring of permanent twilight dividing the fire from the ice. Even in that twilight zone, the sky is violently unstable. Red dwarfs are notorious for their volatile magnetic fields, regularly lashing out with massive bursts of energy called stellar flares. We know what these flares can do. In 1859, the Carrington event slammed into Earth, physically destroying telegraph equipment and shocking operators. Proxima Centauri produces flares that dwarf anything our Sun can generate. In 2019, telescopes caught a super flare erupting from the star that was 14,000 times brighter than its normal output, enough raw radiation to boil away a planet's entire atmosphere. Yet, biology has a stubborn habit of surviving extreme violence. Deep in our own oceans, complex ecosystems thrive off toxic hydrothermal vents, spewing 400-degree chemicals. We routinely find microbial life buried under miles of solid Antarctic ice, metabolizing elements in sub-zero darkness. Life does not require a planetary paradise. If Proxima b possesses a strong magnetic field to deflect the worst of the stellar radiation, its extreme conditions aren't a death sentence. They are the ultimate evolutionary pressure cooker. This animation shows exactly how we found the planet in the first place, the transit method. We pointed a telescope at the star and waited for a tiny dip in the light, a shadow proving something physically crossed in front of it. Now consider the inverse. If an alien civilization evolved in that Terminator zone, their telescopes would detect Earth crossing in front of our Sun. By analyzing that shadow, they could read our atmospheric signatures and identify the oxygen and water vapor. They would know we are here. Our yellow sun will exhaust its fuel and consume the Earth in a few billion years. But Proxima Centauri is a slow-burning engine. Astrophysicists estimate it will continue to shine for another 4 trillion years. That is 290 times the current age of the universe. Long after our sun dies, and long after the rest of the galaxy goes dark, this violently irradiated rock might be the final refuge for biological life in the cosmos. We can theorize from a distance forever, but to know for sure, we must look closely. That is the exact mission of the Breakthrough Starshot initiative. The engineering relies on abandoning heavy chemical rockets entirely. Instead, engineers plan to build microchip-sized spacecraft, attach them to incredibly thin reflective sails, and hit them with an array of massive ground-based lasers. Pumping gigawatts of power into those sails would accelerate the probes to 20% the speed of light, roughly 60,000 kilometers per second. That kind of velocity shrinks a 73,000-year drift into a 20-year sprint. The physics are brutal.
Traveling that fast, a single grain of ambient space dust acts like an artillery shell against the hull. The laser arrays required don't currently exist, yet scientists are actively drafting the blueprints right now. Whether we find a resilient alien ecology huddled in the twilight, or we are looking at the future real estate of our own descendants, reaching this habitable hellscape is the mandatory first test we have to pass to survive as an interstellar species.